Welcome to another lecture. It's our 6th lecture on inverse problems in medical imaging. We are doing something very exciting today, which is the concept of the generalized inverse, which actually allows us to put together everything we have learned in the lecture so far. So it provides a general concept of solving any inverse problems. Let's start. Let's remember the singular value decomposition that we have done in the recent lectures. For a system of equations Gm equals D, that actually yields the decomposition as follows. So G equals U times lambda times Vt, and G equals U P lambda P V P T. And if you remember, this P here defines the number of non-zero eigenvalues. And this comes back to the first equation here, if all of the eigenvalues of are non-zero. U is an n times n orthogonal matrix. Let's write it down here. And actually, each column of U is given by eigenvector UE up to UN, corresponding to the Eve eigenvalue. Similar things go for V, which is an M times M matrix. And our lambda here equals n times m diagonal matrix in this case, containing the singular values. So lambda equals lambda 1 lambda n. Okay. Additionally, we have the information regarding the eigenvalue decomposition, if you remember that, where we have G times G transpose UE, which is the Eve eigenvector corresponding to the Eve eigenvalue. And this equals the eigenvalue times the eigenvector. And also similar for V, we have G transpose G V E equals the eigenvector times VE. Now let's start with a new page. This actually leads us to 4 classes for our system of equations CME based on the matrix size, based on the shape of the vector M and our data vector D. For GM equals D based on P and M. So class 1 What happens if P equals N equals M? We actually know that for this case, the inverse of G exists. The number of non-zero eigenvalues equals the number of the dimension of our square matrix as M equals G. We have a unique solution for our data. And the data, we have a unique solution for M, and the data can be fit exactly. The second class we have is when the number of non-zero eigenvectors equals M lower than N. And this is exactly our least squares problem. So we have an overdetermined system of equations. So more variables than unknowns, which yields to multiple solutions, but only one that actually minimizes the misfit to the data. As it's minimizing the misfit, unfortunately, the data cannot be fit exactly in this case. How does the least squares solution look like? We have the inverse of G transpose G, G transpose D. Now let's come to class 3. What happens if P equals N lower than M? And this is exactly a minimum length solution for M. So our parameters M equal the guy we have derived in the last lectures, which is the estimate expected values of parameters plus G transpose, the inverse of G transpose times a data minus G times the expected model parameters. With this, we can actually fit our data exactly. However, the solution to this is not unique. There's one class of problems missing, which we term the class 4. What happens if the number of non-zero eigenvalues is lower than the minimum of the two vector sizes? And actually, we don't know any way of obtaining the model parameters yet. And actually, this case is the worst thing that can happen because it gives us a non-unique solution. We cannot fit our data exactly. There's no inverse of G. However, most of our real world problems fall exactly into this class of problems. So actually the goal of today's lecture is to find a way to obtain a solution for this class 4. Let's get another page. So our goal for today . We need an inverse operator with following attributes. First of all, we need an inverse operator that reduces to the inverse of G when P equals N equals M. Second, it should reduce to our least square solution, G transpose G inverse G transpose when we have an overdetermined system of equation, meaning P equals M lower N. Third attribute, our inverse operator should reduce to G transpose G transpose inverse when we have an underdetermined system of equations. So P equals N lower than M. And 4, we need an inverse operator that exists for all other cases. When P is lower than minimum M N. To additionally give you an intuition regarding the different sizes and shapes here, let me actually quickly draw here how the dimensions of the matrix G look like, and also of the decomposition U times lambda times V transpose. So we have a matrix G. And actually, so we have here this, in this dimension, we have, it has length P. This guy here has length N minus P. Up here, we have N entries. Now let's have a look at the lambda part. So we have the diagonal matrix for lambda for all those with non-zero eigenvalues and zeros all elsewhere. And this is actually size P, M minus P here. And in this dimension, also P and minus P. This multiplied by VP transpose, V0 transpose. Again, this holds the entries for the eigenvalues with 0, which are 0. So we have here the dimensions P here, M minus P here, and m in x direction. So just to remember, if P equals N equals M, we have G equals U lambda V transpose, where all eigenvalues are larger than 0. So the absolute value of lambda 1 is larger or equal absolute value of lambda 2, and so on, larger or equal lambda n, larger than 0, which means the inverse of GE exists. So we get the inverse of G equals V transpose inverse lambda inverse of U with lambda inverse equals a diagonal matrix 1 over lambda 1 up to 1 over lambda n, which exists because we have no 0 eigenvalues. Additionally, U and V are orthogonal. So we get the relationship V, the inverse of V transpose equals V, and U inverse of U equals U transpose, which gets us the final inverse of G equals V times the inverse of lambda times U if we have a square matrix for G and no 0-valued eigenvalues. So this is the first important solution for today. Let's continue on a new page. So we have found now the operator for our squared matrix M, where the inverse G exists. So we want to find the operator for the 3 remaining classes. That will reduce to inverse of G when it exists. And this exactly leads us to the generalized inverse operator, which we term here GG to the power of -1. And this is actually exactly the so-called pseudo-inverse or Muir-Penrose inverse, which you might have already heard of. And this similar notation, Muir-Penrose inverse, pseudo inverse, which is given by G and this dagger symbol. Okay, let's start. So again, we have here now the decomposition of G to U lambda V transpose, and we just show the inverse of G equals V inverse of lambda U transpose if inverse exists. And now we also have that we can decompose G to UP lambda P VP transpose, so singular value decomposition, where P again equals the number of non-zero eigenvalues. Let's start to introduce the generalized inverse operator. Which is G minus 1. Okay, quick recap what we had just done before. Class 1, we had P equal N equal M. So all eigenvalues are non-zero. So we have VP equals V, UP equals U, lambda P equals lambda. So this is the guy what we just showed. G inverse equals V times lambda to the power of -1 U transpose. So we are all set. Class 2, which is our least squares problem, where we have P equals M lower than N. What we have now is VP equals to V. For U, we have now UP, U0, because this set now is not empty. Let's also recall the least squares solution, MLS, equals G transpose G to the power of -1, G transpose D. And actually, it's now very easy to show what this guy in here is. We don't do this now in the lecture, but you can do it easily on your own. So G transpose G equals exactly VP square VP transpose. So if P equals M, so the dimensions match here, G transpose, the inverse of G transpose G exists. We just have to invert this guy here. Just G transpose to the power of -1 equals VP transpose -1 lambda P to the power of -2 VP to the power of -1. And we can again use the concept of orthogonal matrices here, which means this reduces to Vp lambda p to the power of -1 Vp transpose. And now what we have just shown is that the general inverse operator is equivalent to the least square solution when p equals m, and this is lower than n. So let's put this all together. So the equivalence the general inverse operator and least squares when p equals m, lower n. So the least squares GLS equals to G transpose G to the power of -1, G transpose. Now let's simply plug in here what we all know, which is Vp lambda p to the power of -2 Vp transpose. And for G transpose, it's Up lambda p Vp transpose. This is exactly Vp lambda p to the power of -2 Vp transpose. And we know if we transpose this here, it's actually transposing the single elements and turn around the order. So we have Vp transpose, it actually gets back to Vp. Lambda p transpose and lambda all the same. And we have left Up transpose, which means this guy here is identity. Then we have here left, let's write it out. Vp lambda p -2 Vp, oops, no, this is not Vp, it's lambda p Up transpose. And this again, we can merge together, equals Vp lambda p -1 Upt equals our general inverse operator. So if p equals m lower n, the generalized inverse operator is equivalent to the least squares operator. So we are all set here. Now let's move on to class 3. So we have now p equals n lower m. So what we have now is Up equals U. V is defined as Vp V0, where V0 is not empty. So we have here now our underdetermined system of equations, and we need to recall the minimum length solution. which equals G transpose and the inverse of G transpose. And also G times G transpose equals UP lambda P VP transpose times UP lambda P VP transpose. If we write this out, we have UP lambda P VP transpose VP lambda P UP transpose equals UP lambda P squared, because this guy here again goes to identity, UP transpose. So if P equals N, the inverse of G3 transpose exists and is defined as UP lambda P squared UP transpose to the power of -1. And this equals UP lambda P to the power of -2 UP transpose. What we can do then is to plug it into our minimum length operator, GML. So GT, the inverse of GT to the power of -1 equals UP lambda P VP transpose UP lambda P to the power of -1 UP transpose equals VP lambda P UP transpose. So the same concept of transposing this individual matrices here as before. What's left is UP lambda P to the power of -1 UP transpose. So this goes to identity. This guy's here. We can merge together to lambda P to the power of -1. So what's left now is VP lambda P to the power of -1 UP T. And this equals, again, our generalized inverse operator. So what we have just shown is that if the dimensions P equals N lower M, the generalized inverse operator is equivalent to the minimum length operator. So, and now the most interesting part is missing, right? It's the class 4, where most of our real world problems go into. And this is when P is lower the minimum of the dimensions Mn. So in this case, G transpose G inverse And the inverse of G transpose power of -1 do not exist, which means there is no least squares or minimum length solution. And we have a number of 0 eigenvalues, which means also that U equals UP U0 and V equals VP V0, where U0 is not empty and V0 is not empty. Which means the generalized inverse operator cannot be further reduced. So the solution, which stays here, is generalized inverse operator is defined as Vp lambda p to the power of -1 UP_t. And what this actually does, it simultaneously minimizes the misfit vector and the solution length. And what we additionally can say here, that the solution is not unique and the data is not fit exactly. Okay, so what we have found now is really a general concept to handle all classes of problems that we have tackled so far, plus the one which is mostly related to our real world problems, which is really exciting to show this via singular value decomposition, so that we are able now to solve all kinds of problems. We will touch a second topic for today, where we move to nonlinear inverse problems. So far, we have only considered linear forward problems of this form, G times M equals D, where the matrix G consists of coefficients, and we have the two vectors M, where M is the model parameter vector and D the data vector. And this can be written explicitly as Di equals the sum over J equals 1 to M, and Giy Mj, where I equals 1 to N, showing you the linear nature of the problem. So what do we have to do now if we want to consider nonlinear forward problems? So Di equals Gi as a function of M. And the goal here is to linearize this such that we can solve this. Step one, the nonlinear forward problem again. to have everything here. Ei equals Gi of M. Okay. Step 1. Do you have any ideas how we can actually linearize this guy here? What we can do is to expand GIM about some point M0 using Taylor expansion. Let's just recall the Taylor series. We can decompose any function fx into the sum of n equals 0 to infinity f to the power of n about some point a divided by n factorial x minus a, oops, to the power of n. If we want to do this now here, we expand Gi of m about some point M0 using Taylor series. So we can write Ei equals Gi of m, and this is approximately Gi evaluated at M0 plus the sum Gi equals 1 to m, the derivative of Gi with respect to mj evaluated at m equals M0 times delta mj, which equals exactly m minus M0 in this case for this step, plus second order derivative 1/2 sum of j equals m equals 1 to m. Second order derivative of Gi with respect to mj squared at m equals M0 times delta mj squared plus higher order terms. And we said that delta m equals m minus our starting point M0. If we can assume that the higher order terms are small, we actually use only the Taylor series up to the first order. So if the delta mj n for n lower equal to are small, we use only di equals Gi of m and approximate it with Gi evaluated at M0 plus the sum of j equals 1 to m. The first derivative, dGi with respect to tmj at m equals M0 delta mj. That was step 1. Step 2. What do we have to do next? Now we can determine the predicted data D hat. At m equals m0. And these are given by di hat equals gi of m0 So actually, this is di minus di hat. So we take this guy here. This is our d hat. And say this approximately equal to g equals 1 to m. First order derivative. So gi m with respect to tmj evaluated at m equals m0 times delta mj. Okay. Step 3. We can now define the new misfit. Delta ci as exactly the difference of di minus di hat, which is actually the observed data minus the predicted data. Okay, now we're getting closer to the end of the steps here. We define the 4th step for linearizing the nonlinear problem. We define now gij equals the first order derivative gim with respect to tmj at m equals m0. And in the last step, we combine everything that we have gotten so far. So we can define our misfit delta ci as the sum over j equals 1 to m gij delta mj evaluated at m equals m0 for I from 1 to n. And now let's get back to matrix notation. We actually have nothing else than delta c equals g times delta m, where delta ci equals di minus di hat equals di minus gi evaluated at 0 Gij equals first order derivative of Gim with respect to J evaluated equals 0 and delta J equals J minus M0 J. So actually, we have now derived a set of linear equations where this delta Ci is now a linear function. And what we have done is we have derived this linearization only in a neighborhood of M0. And another thing that we have to note that this G we introduced here changes now with every iteration, which makes it computationally very, very expensive. So how does the general procedure now look like to solve this? So first of all, we need to pick a starting model vector M0. Using this, we can then calculate the predicted data vector E hat and the misfit vector delta C equals to the observed data E minus the predicted data D hat. We then form Gij as the first order derivatives, as a matrix of first order derivatives of the Gi of M with respect to Mj evaluated at our starting vector M0. We here then solve for delta C equals G times delta M using an appropriate inverse operator here. And in the last step, we form now the new model parameter vector M1 equals M0 plus this delta M we just got from solving this problem. And these steps have to be repeated until this delta M becomes very small, which means that it converges, or the delta C becomes very small, which means the error between the observed and the predicted data becomes acceptable. So while this looks very cumbersome, let's do this for a number of examples to show you how this works. And let's start here with the first example. Where we consider a linear problem. So we say that 2m equals 4. And obviously m should equal 2, but let's make the calculation step by step. So what we need is we need to have g, and this is the first order derivative with respect to m. So what's left here is 2m first order derivative. So we just have 2 left, and our observed data equals 4. And this holds for every iteration m. So because the g is not dependent of m anymore. So d, g, 1 with respect to T D M1, G11 equals 2 for all I. Let's suppose we start at 0. M0 equals 0. So the predicted data equals G0 equals 0. And we then get the delta C is the difference between the observed minus the predicted data is 4 minus 0 equals 4 equals delta C1. So G11 times delta M1 equals delta C1. So 2 delta M1 should equal to 4, which leaves us with delta M1 equals 2. And our model update gets done. M1 equals M0 plus delta M1. This is 0, our starting point, plus 2. Predicted data gets now G1 is G is 2 times 2 is equals 4. And then our delta C is D minus D hat. 4 minus 4 equals 0. And this guy converged within a single step. So what you could try by yourself is to select a different point for M0, and you will still see that it will converge within a single step for the linear problem here. Let's consider a nonlinear example. And this time we're using 2m to the power of 3 equals 16. And obviously the solution for m is here too, but we will solve this now through this iterative procedure we just wrote down before. So first note here, G11, the first order derivative of Gm with respect to dm evaluated at some position mi. So this I here denotes the iteration for which we are solving. And this is obviously, so we are deriving this part 3 times 2mi squared. So it's 6mi squared. Okay. Let's start at iteration 1. So we start with our initial point m0 equals 1. Okay, let's look at G11. 6 times 1 squared equals 6. Our predicted data is then 2 times 1 to the power of 3 equals 2. And delta C becomes the misfit of the observed data minus the predicted data equals 16 minus 2 equals 14. Additionally, note what happens if we square this misfit here. This becomes 196. Now, as we have that, we solve now for G 6 times delta M1 equals delta C, which is 14. So we get here delta M1 equals 14 over 6. Such that we get M1 equals M0 plus delta M1 equals 1 plus 14 over 6 equals 3.3 periodic. Okay, let's continue with iteration 2. Again, our G equals 6 times M, in this case 1 squared. So this equals to 66.6 periodic. So for M1, we use the 3.3 we got before. Our predicted data becomes now 2 times 3.3 periodic squared equals 74.07. And this gives us the delta C of the observed minus the predicted data equals 16 minus 74.07 equals minus 58.07. And delta C becomes 3,372. Actually, we observed that this point here gets now larger, right? So what we can then estimate is the delta M2 from this G11. So 66.6 periodic times L delta M2 equals minus 58.07. So this is G times delta M2 equals delta C. And we get our update for M2 is M1 plus delta M2, which equals 2.462. You can already see this is pretty cumbersome, even if we already know the solution. But let's continue with the next iteration to obtain our final model parameter M. So we have now G11 equals 6M M2 squared. So we plug in the M2 from before, yielding 36.37. And now our predicted data equals to 29.847. This gives us a new delta C of minus 13.847. And also let's look at the squared error. Which now reduces to 192. Moreover, we can again calculate delta M3, which is G of 36.37, delta M3 equals minus 13.847. So we get for delta M3 minus 0.381. And M3 turns now M2 plus delta M3 to 2.081. So we're getting closer. We need another iteration. Four. So G1 equals 6. 3 square equals 25.983. And the prediction D hat equals 18.024, yielding our delta C of minus 2.0224. Delta C square is now 4.1. And now solving again for delta M4. The same as before. And we will see that we get again closer to our solution. So delta M4 equals minus 0.078 and M4 then equals 2.003. Not much left. So in the next iteration, we will get there. So G equals 6, 4 square equals 24.072. The prediction D hat equals 16.072. This gives us a delta C of minus 0.072. And the delta C square of 0.005. We can now solve for the delta 5 equals minus 0.072. And delta 5 is now minus 0.003. And we get M5 is 2. So within 5 iterations of this algorithm, we then get to the obvious solution of 2. Let's just check for sure if we really converge to our solution. In the last iteration, so we get G11 is 6, M5 squared equals 24. The prediction is now 16. We know that our observed data is 16. So delta C equals 0. And we finally converged. And this is actually already the end of today's lecture. So we handled today 2 large topics, which were the generalized inverse operator, also known as the Muir-Penrose inverse, pseudo-inverse, which introduced a concept to gives us a solution for any matrix G. And we also did nonlinear Fourier problems and found some kind of linearization, developed an algorithm to actually get to solutions for nonlinear problems. Are there any questions? Does it always converge? I think there's diverse conditions for this case. Let's go back. So actually, I mean, it depends. We can observe this delta M and the delta C. So it can happen that this delta M, that this does not converge to any point, but we stop, for example, when delta C becomes small enough such that we can accept the misfit